Well, first of all, I want to take the opportunity to really thank the organizers for the event and for having us here. It's been very, very fruitful for us and for me especially. And the open communication, I think, is really important. So we do hope to continue this open communication. What I'm going to go through now is this design of example, the building one, also showing what would be a code-based design, and then going through a few more steps on the objective-based design as well for you guys. So, as was described already, this in the slides that you have, you will see only the imperial units, but then I've added also the SI unit. So Arta will be distributing later so that you all have access to this as well. But here is information. Maybe I'll go down to what was brought up, that we are using 150 pounds per square foot, which is equivalent to the 7.2 kilonewton per meter squared here in terms of load. And then we're using also the Denali earthquake. That's our basis earthquake for our design. And this is the code-based design is going to be done using ASCE 716 and ACI 318.19 as well. So we have both the maximum considered earthquake, that's the one in blue, and the design basis or design earthquake, which is the one in red. On top there is the spectral response spectra, and then on the bottom, we've been just making sure that we look at this because it really makes it really clear that slight shifts in period really doesn't impact your spectral velocity. So you can consider that as always a basis of design, because small adjustments in that period is only really not having a big impact there on your spectral velocity. So going a little bit more in detail, so this was taking this building design and placing it for a second in California. And so in California, what is typical is 8-inch slabs. These are post-tension concrete slabs, so that's our basis of our design. We didn't do a detailed design for the slabs, but that would be the base for the building. We are considering that it's a special reinforced concrete moment frames, which is going to bring to an R factor similar to yours that I saw in the design, R factor of 8 as well. And then these are our sizes. So our beam sizes, width 71 centimeters and about a meter, 102 centimeter deep. That's including the 20 centimeters for the slabs. So similar in the ballpark of what you guys were getting as well. And then the typical column size, 76 by 91. Notice here we have this MF, so for the moment frame. I don't think it's the way you design here. It's not the way it's done in the Eurocodes, but it is the way it's done in the US, where you have the lateral resisting system that you design specifically for your lateral loads. And all the other elements are designed for gravity loads. I don't know if you want to say that or...
Evet, dış çerçevedeki bu Eurocode'da da olmayan bir özellikten bahsetti Profesör Barbosa. Özellikle Amerika'da dış çerçeve güçlü bir dış çerçevemiz var ve bu dış çerçevenin içerisindeki diğer elemanlar sadece düşey yüklere göre tasarlanıyor. Fakat dış çerçeve perde duvarları değil, sadece dış çerçeve, güçlü bir dış çerçeve deprem yüklerine karşı tasarlanıyor.
Okay. So those are our moment resisting frame sizes by code, and this is a typical concrete strength. So for slab, beams and columns for the moment frame, around 6,000 KSI, so 40 megapascal, and then for the other columns, and beams would be 35 megapascal. For the beam and columns, for the code-based design, we had to consider a little bit more capacity. So it was also specified that it would be at 80 days around 55 megapascal. So accounting for that increase in strength as time goes on, and that was needed for the dimensions that are here. In terms of reinforcing steel, grade 80, especially in California and in the West Coast of the United States. There's a big push for use of grade 80 reinforcing steel as well, mainly because of the decongestion in those beam column joints.
Evet, bir de şu husus var, diyor Kaliforniya'da özellikle 550 megapaskallık yüksek kapasiteli bir donatı çeliği kullanılıyor. Çünkü oradaki bu tabii donatı çok fazla olduğu için, olabileceği için daha doğrusu, onu biraz daha azaltmaya yönelik bir çalışma oluyor tabii ki 550 megapaskal.
And then for column rebars and ties, in general, it was 60 KSI, so 415 megapascal. For the other elements that are not designed for lateral resisting forces, are designed for gravity. For example, the columns, and I'll mention a little bit more, but the columns, we can design them by 56 by 56.
Evet, kolonlar da tabii dış çerçevelerin dışındaki, içerideki kolonlarda daha ufak ebatlarda 56'ya 56 olarak öngörülmüş.
Okay, so for the code-based design, what we ended up requiring was 6 bays in each direction. So 1, 2, 3, 1, 2, 3. So a total of 6 bays in each direction. And the period that we're obtaining was 0.95, 0.93 in the east-west, north-south direction. In the code, recently, the limit has actually gone down to 2%. So unlike the 2.5% that you guys are using and we use also for the objective displacement design, the code mandates that it would be 2% maximum.
Evet, bu tabii ki şartnameye göre konuştuğumuzda şartnamede şu andaki limitimiz 2 olarak belirlenmiş olup bulunan periyotlar zaten yukarıda yazılıyor. Seismic Beşir'de %15 kadar çıkmış. Bunu alınıyor daha doğrusu. Evet.
But it's a magic number because up to 4 stories we can design to 2.5. 5 stories, no, 2%, right? So I'm sure there's a big science behind that number.
Burada tabii ki 4 ve 5 katlı binalarda da 2-2,5'a çıkıveriyor birden. O da tabii ki nasıl bir şey, çok böyle hani magic bir şekilde çıkıyor diyor Profesör Barbosa.
And so with that, our seismic base shear would be around 0.15 there. We can get back to this, but in terms of reinforcing, just I think what's typical, we do go with a reinforcement through the beam column joints, the reinforcement in the columns, and this is just a typical reinforcing, and then usually at the ends of the beams, tighter spacing, and you should have all the details printed out for you as well. In terms of, maybe to point out, in terms of the beam reinforcing, use a lot the 2-layer so that you improve the spacing for the concrete.
Evet, girişlerde de 2 kat donatı kullanılıyor ki burada biraz daha tabii oradaki donatı açıklığını rahatlatmak üzere.
And as part of the design process, detailing, an initial detailing of the beam column joint goes a long way to avoid a lot of iterations later. So early, even in the preliminary design, start developing these sketches so that really you get a full perspective of can it actually be buildable. And at the bottom there, this is the columns that are part of the moment resisting frame, and these are the gravity columns.
Evet, alttakiler iç mekanda kullanılan kolonlar. Yukarıdaki ise moment resisting frame'in kolonları.
Okay. So, in terms of the objective-based design, what I want to bring up is that really you need 2 sheets of paper, right, in order to do the sizing of your elements.
Sadece 2 sayfayla biz bu işi objective-based design metoduyla yapabiliyoruz.
Right, and so if you go through the steps that Bob had explained before yesterday, here are all the steps. And first step is you define your target drift. You may see there that it's 2.5% for 5 stories. These are in feet, but the 13.1 feet is 4 meters tall. You go and you define your target displacement, and there the numbers, let me see if I can point, but it's a 2.5% times the number of stories times the height of the building. So that's how you define your value there. Bob yesterday joked that Chopra had written this equation about 100 years ago. It's probably close to 50, but this is your participation factor to account for the mode shapes. And so 1.36 for gamma. And from there, you establish your objective spectral displacement, which is just the target divided by gamma. And so in this case would be 14.45 inches. I have these numbers summarized in metric later as well. Then we're using this Denali earthquake in terms of spectral velocity, defined 60 inches per second, so about 150 centimeters per second, or 1,500 millimeters per second. And with that, you define your period there just by spectral displacement divided by spectral velocity times 2 pi. And so that you have your target value. So very close to what you had, 1.54, 1.5 here.
So, daha evvelden sizlerin de bulduğu 1.54'e göre buradaki metotla da bulunan 1,5 saniye aslında çok yakın çıkmış. Burada tabii bir etap bir gidişat var, bir prosedür var. İlkin %2,5 drift kabul ediliyor. Ve bundan sonra da tabii ki 5 katlı bir bina n eşittir 5 oluyor. Ve buradan bir hedef deplasman hesaplanıyor ki o da 20 inç civarında. Daha sonra bu Çopra'nın 50 sene evvel bulduğu ki Profesör Engelkök de biraz hani orada bir şey yaptı. 100 sene evvelki şey dedi ki bayağı eski bir formülasyondan bahsediyoruz. Lambda formülü kata bağımlı olarak bir katsayı 1.36 çıkıyor ve delta t'yi de lambda'ya böldüğümüz zaman da bir spektral deplasman ortaya çıkıyor. 14,5 inç olarak. Daha sonra da bu tabii ki hız spektrumu devreye giriyor. Ve oradan da işte SV'yi buluyoruz. Yani spektral hızı 60 inç bölü saniye olarak hesaplanıp daha sonra da bizim periyot hesabımıza girecek olan rakamlar ortaya çıkıyor. Periyodumuzun da 1,5 saniye olarak olduğu ortaya çıkıyor. Evet.
Thank you. Then you need to have an estimate of the sizes that you're going to use for the building. And these sizes were selected based on, Bob had shared yesterday, and you also have the SSRP report. In that SSRP report, table 3.2, there's steps to define the initial dimensions or an estimate of the dimensions that match this period. So very simple equations that go back to fundamental structural analysis, and it's a parametric equation to define for, if you imagine a beam that's hinged at halfway, columns hinged at halfway their story height, you apply a deformation, and with that you can size all your members based on the target period that you have as well. So it's a way to size your elements, but you need to size them somehow, however you think.
Sorry, do you mean the portal method?
Portal method, essentially.
For the distribution of internal forces, approximate distribution of the internal forces between the members.
But just assuming a beam column, right? Hinges located at midspan, and then that's it. Yeah.
The approximate method.
An approximate method to come up with the dimensions to match the period, right? But you can use other methods. You can use the computer. You can do whatever you want to come up with those initial dimensions. But this just makes sense to have this as a basis for
Evet,
that.
yani bu periyodu tabii tutturabilmek için bu 1,5 saniye hesapladık. Şimdi 1,5 saniyeyi verebilecek olan kolon ve kiriş boyutları ne olmalı? Bunun içinde hocamızın da söylediği portal metodu olabilir veya bizlerin gayet iyi bildiğimiz approximate metot, yani tahmini veya yaklaşık metotlarla çözdüğümüz bir yöntem vardı biliyorsunuz. Kolonların ve kirişlerin sıfır moment bölgeleri ortalarda idi. Tabii bunu izostatik sisteme çeviriyoruz sistemi ve dolayısıyla buradan da bir sonuç çıkabiliyor. Fakat hani bilgisayarla da yapabilirsiniz dedi Profesör Barbosa. Ama buradaki olay 1,5 saniyeyi verebilecek bir çerçeveden bahsediyoruz. Yani o şeylerin, kolonun ve kirişin ebatlarından bahsediyoruz.
This step takes a little bit longer than just a line, because this is, you develop your SAP 2000 model or your ETABS model, and then apply the loads, the masses, the dimensions that you have. And the initial period estimated was about 1.2 seconds, just putting these dimensions into ETABS.
Evet. Yani bu da ETABS modeliyle de çözülmüş. Burada da bu biraz daha tabii uzun sürüyor çünkü modelleme var. Her ne kadar bu sistem yani el hesabı olsa da o modelden çıkacak olan ki o modelin içerisine de tabii ki kolon kiriş ebatları da giriyor. Ve oradan çıkan sonuçta da 1,2 saniye bulunmuş.
Now, at this step in the design, you could do one of two things. One thing would be to adjust the dimensions so that your period matches 1.5 seconds. Maybe you want to say that, please.
İki yöntem olabilir bundan sonraki etaplarda. Bir tanesi bu kolon ve kirişleri biraz daha modifiye ederek, büyüterek veya küçülterek 1,5 saniyeye erişebiliriz.
Okay. Here, just like you had adopted, assuming that there is some period lengthening as you go to higher drifts, and assuming that value, then it would be closer to 1.4. But still at the 1.4, we haven't really reached the 1.5 target. So you could go in and change your sections such that you would get closer to your target values.
So you're multiplying the period which you found in your ETABS solution
In this case,
by augmenting like 20%,
15, something like that. Mm-hmm.
Sort of get this or try to reach this estimated or
Right.
target period.
It's a lever that you can use or just adjust the dimensions. Yep.
Evet. Ya işte hani boyutları yaparak adjust ederek veya periyodu %20, %25, %15 gibi bir rakamla arttırıp 1,5'e belki de getirebilirsiniz diyor.
Okay.
Evet.
This step, I'm putting it here because there were questions of if you want to estimate forces. I know Bob is going to have some opinions on that, but here you are estimating also spectral accelerations directly from spectral velocity. And here is your specified period. Okay, so you had the target period T sub T. Here is the specified period that we're now working with.
Evet, yükleri tabii ki günün sonunda yükleri bulmamız gerekiyor. Dolayısıyla spektral ivmeyi hesaplayabiliyoruz. Burada da artık daha evvelden bulunan 1,5 saniyede değil de biz aslında ya 1,5 saniyeyi verebilecek kolon kirişleri modifiye ettikten sonraki periyodumuz veya %20 ile arttırdığımız periyot neyse onunla hesaplıyoruz. Artık şu anda yolumuza yeni periyotla gidiyoruz.
And that gave us around 0.7 G.
Bu da zaten 0.7 G'ye tekabül ediyor.
In terms, you then estimate your effective mass, another equation that you can go look up Chopra or any other method that you want to use.
Evet, bir başka terimde buradaki bir model kütlenin bulunması. O da zaten Chopra'da da var veya başka yöntemlerde, empirik formüllerde de bulunabiliyor. Model kütleyi de bu şekilde hesaplıyoruz.
And with that, you estimate about what you had, 0.8, 0.82 in terms of your effective model mass. Then ductility factor, R factor, whatever you want to call it. Here we're using the value of 8.
Evet, ductility yani süneklik katsayısı veya R katsayısı nasıl siz söylüyorsanız bunu da 8 olarak biz seçiyoruz bu bina üzerinde.
And with that you get your base year of about 0.07.
Bundan sonraki etapta da tabii ki bu R faktörüne böldüğümüzde de hepimizin bildiği gibi bir base year hesaplanıyor. O da işte ağırlığın %7'si kadar bir taban kesme kuvveti ortaya çıkıyor.
So in the end, your specified period drives your effective base year. And because we're basing this on spectral velocity, we're being consistent also with estimating of spectral acceleration, spectral displacement that you would use for checking your design.
Evet. Tabii ki günün sonunda bu ikinci etapta hesapladığımız periyottan bu base year ortaya çıkıyor. Ve bu da zaten spektral ivme ile uyumlu bir figür.
Okay. So here's the summary. So it looks a little bit better. So we have our spectral velocity of 150 centimeters per second. That's our target drift. This was our target period, although I've shown how we could use another value. For this, instead of the 3 bays for the lateral resisting system, we only need 2 bays instead of 3. And for the moment resisting frame, and the sizes are similar. So 71 by 102 and 76 by 91 for the columns. The typical concrete strength, we did not have to use the extra capacity, the 8,000 PSI, so we could just do the 40.1 megapascal for the concrete strength, and that was our base year here at the base.
So you sort of optimized the number of bays in this case.
Yep.
So instead of 3, you reduced down to 2.
Yep.
Okay. Evet, burada bir ufak bir optimizasyon yapılmış sanırım en sonunda. 3 B'den 2 B'ye inmiş. Yine tabii ki 4 ana çerçeve var. Ve bunlarla birlikte bir dizayn bir şekilde bitirilmiş. Özeti de zaten yukarıda. İşte aldığı değerler %2,5 limit. Target 1,5 saniye. Ve o 1,5 saniyeyi verebilecek kolon ve kiriş ebatları ve sonunda da kesme kuvveti, taban kesme kuvveti de ağırlığın %7'si olarak hesaplanmış.
And one less bay, and that is moment resisting frame there.
Bu da moment resisting frame. So this is your output out of OBD.
I'll show the SAP model
Okay.
as well. So we put this into our SAP model, and then we do the design based
Okay.
on it.
So this is supposed to be less reinforced
In general, because we have fewer columns.
when you compare with the code based.
Yeah, because we have fewer columns that are moment resisting columns, right? So the sizes, fewer columns that have the larger sizes. And then the other beams are designed for deformation compatibility. I'll explain that as well. But overall, a smaller building in terms of structural elements.
Yes. Okay, please go ahead.
So here, a summary of our code-based design versus the objective-based design. As I had mentioned, in terms of the drift limits now, for the 5-story building, it's 2%. That's our period. We needed 6 bays. Sizes of beams and columns are here. As I mentioned, the concrete strength and 0.15 for the seismic coefficient. And then on the right, the objective-based design, the 2.5% drift, 1.5 for the period, 4 bays, 2 bays per frame. In this case, we had similar beams and column sizes, but fewer bays. We didn't have to take into account additional capacity for the concrete and 0.07. Then for the gravity, I didn't mention much of that before, but for the gravity columns, here again are the dimensions. We would also have similar beams and similar column grid, and this is an example beam size that you'd have to check for deformation compatibility.
Evet, sonunda da böyle bir mukayese tablosu önümüze çıkıyor. Şartname ile ilgili kısımda 4 B'ye yani 4 açıklığa ihtiyacımız oluyor. Yani daha doğrusu 3 açıklıklı 4 adet moment resisting frame'e ihtiyacımız oluyor. Diğerinde de 2 açıklıklı 4 adet moment resisting çerçeve ihtiyacımız oluyor. Burada önemli bir tabii mesafe kat etmişler. Aynı zamanda periyot tabii ki uzuyor. 0.95'ten 1.5'a kadar bir periyot aralığı var. Genişlemesi var. Tabii bu da taban kesmeye önemli ölçüde azaltıyor. %15'ten %7'ye bir düşüş var. Aşağıdaki rakamlar da kolonların ve kirişlerin ebatları. I may have one question. Have you mentioned about the percentage of steel? Have you kept it at 1% reinforcement ratio?
Yeah.
Yes.
Yeah.
Okay. Burada da %1 oranında bir donatı oranı olmuş ve onu sanırım sabit tutmuşlar.
What about the beams? Beams ratio?
Similar.
Similar.
Yeah. Just to explain, because this may be new for you, maybe not, but just adding these 3 bullet points here at the bottom. In what do we mean by this deformation compatibility check for the non-lateral resisting elements?
Tabii ki bunları yaptıktan sonra da bir takım fiziksel deformasyonlar, yani bu işte bunların da bir çekleri gerekiyor elbette.
Yeah.
For serviceability purposes.
No, for seismic.
For seismic, okay.
For seismic as well. So we didn't design them to take loads, but they're going to go along
Okay.
for the ride, right? So we do have to check for that design. We have to check the moment curvature. So this is one of 3 ways that you can do a moment curvature analysis to determine the deformation compatibility of your gravity system, and then check and do capacity-based design for the induced shear forces as well. So that's one way. You size your element, you put the reinforcing steel, and then you do a moment curvature analysis and make sure that the detailing is such that you can get to that deformation. Another way, ACI 318, if you're not doing a moment curvature analysis, even though from what I know, most companies do moment curvature analysis, but should I stop?
Burada 3 değişik yöntemle bu çeki yapabiliyorsunuz. Birincisi moment curvature'la, yani moment kapa ilişkisiyle bir deformasyon bulabiliyoruz. Eğer bunu yapmıyorsak ki çoğu firmalar bu moment curvature'la çalışıyorlar zaten, ama bunu eğer tercih etmiyorsak diğer 2 yöntem de mevcut.
So if you don't run moment curvature analysis, then there's these 2 clauses in ACI 318, which is an easy and quick way to account for deformation compatibility. So you have additional detailing requirements for those beam column connections. Otherwise, which I think is what you typically do, or closer to what you typically do in Turkey, you consider them also in your final element software, and then you check moments and shear, but please do check that you're doing good detailing so that you do reach the curvature needed as well. So there's the 3 different ways, so a different design concept, but I wanted to make sure that we had it all laid out there as well.
Evet, burada tabii 3 değişik yöntemle bunu kontrolleri yapıyoruz. Daha evvelden de dediğimiz gibi moment curvature olabilir veya ACI'nin daha basit bir 2 formülasyonuyla yapılabiliyor. Veya bilgisayar analizlerinde işte bu sonlu elemanlar yöntemiyle de bu çekler yapılabiliyor. Yani kesme ve momentten dolayı meydana gelen bir takım deformasyonlar burada da yapılabiliyor.
Okay, so now that we have these 2 different designs, we went to do a performance check. We're going to show you some results of nonlinear time history analysis for both buildings. We're going to run them at the 100% MCE level, and we used ETABS to run these analyses, and we're modeling the building moment resisting frames. And then, as I mentioned, these are the additional checks that we would have to do for the gravity. So per ACI, and I think from what I was noticing is what you guys do here as well. So you use the effective stiffness, 0.7 high gross and 0.35. And then we modeled the hinges and do moment curvature analysis for the beams to develop our moment rotation backbone for the beam hinges. And the beam hinges were defined as moment M3 hinge, deformation controlled hinge in ETABS. And depending on the reinforcement, slightly different reinforcement, we have 3 different beams. Here are the parameters actually assigned in the code-based design versus the objective-based design. And one thing that you can already see in the hinge is that in terms of the allowable, the maximum values that you're allowed, and even this initial value here for the elastic deformation, they're very close, but you can have slightly different values there. But anyway, this went into the model, and then I'm going to try to show this video. Let's see if this starts. Is it running? There we go. So displacement response, this is the interstory drift ratios, base shear, and overturning. The overturning is based on one of the axes of the building. That's why it starts as a non-zero. And this is the actual ground motion. So you're going to see just the development of the peak interstory drifts here at the 3rd story, and typical base shear forces and overturning there as well. So the peak floor accelerations of about 0.7 g, 34.5 centimeters maximum roof displacement. The maximum interstory drift was 2.25 per the nonlinear model, so a little bit above the 2% that we had defined, but yeah, in the code. But this is the nonlinear time history response analysis for one earthquake only. The base shear, and this was the maximum rotation in the roof hinge, about 0.6%. Level 4 and level 3, 1.3%, and 0.8 at level 1, level 2. The beam hinges underwent plastic rotations, but they were well within the collapse limits there. And the residual drift for the code-based design was 0.5% interstory drift ratio. These numbers, like any other numbers, are based on this model. And I don't know how much you trust roof residual displacement predictions, but it's the prediction from this model that we have here.
Sadece bir deprem özelinde yapılmış bir çalışma. Non-linear time history, yani zaman tanım alanında yapılmış bir çalışmada. Bu değerler saptanmış. Bunları bir okumayayım. Buradaki interstory drift de biraz değindi. 2.25, işte 2'nin biraz üstünde, ama yine de böyle bir sonuç, bu deprem üzerinde böyle bir sonuç elde ettik dedim.
Okay. Then we ran the same, the adjusted model, but we ran the nonlinear time history analysis. Similar type of response. I could show the video. In the interest of time, I think I'll skip the video here and go straight to the results. Very similar in terms of our peak floor accelerations. The maximum roof displacement was a little bit higher, 43.2. So instead of 2.25 for that code-based design, we have a prediction of 2.8% for this model. Base shear, the hinge rotations also a little bit larger. So instead of 0.6, now it's 0.8. Instead of 1.3, 1.6, and about 1% rotation for level 2, level 1. Similar conclusion, still very far from reaching any collapse limit, and the residual drift was a little bit higher as well. Overall, with this softer system, you would expect to see a little bit higher drifts.
Evet, bu iki beyli bir, yani iki gözlü bir moment resisting frame sisteminde de bu sonuç biraz daha tabii soft bir sistem olmasından dolayı driftler tabii ki biraz daha fazla çıktı. Ama yine de kolaps, yani bu göçmenin den daha evvelki bir zamandayız. Yani göçme aslında olmamış. Diğer modelle benzer bir davranış sergilenmiş.
So, a summary here set as advantages, but overall it's a summary. Buildings designed with objective-based approach need to withstand nearly half the seismic base shear forces compared to those designed using code-based method. That's one first conclusion. We saw 0.15 versus 0.07 for the seismic coefficient.
Evet, önemli bir bu tabii ki object-based design yönteminin avantajlarından bahsediyoruz bir özet olarak. Buradaki en önemli nokta taban kesme kuvvetlerinin neredeyse yarısı kadar bir değerle çalışıyoruz.
With the same element sizes, same column sizes, same beam sizes for the moment resisting frame and for the gravity columns, the objective-based design was effective with a 4-bay frame, so 2 plus 2 in each direction, as opposed to the 6-bay frame required by the code-based design.
Evet, bu da tabii ki bir başka, her şey aynı olmak kaydıyla, yani bütün kolon ve kiriş ebatları aynı olmak kaydıyla buradaki moment resisting çerçevedeki bay sayısı, yani göz sayısı 3'ten 2'ye düşüp tabii iki tarafları olduğu için binanın önemli bir tabii ki burada bir oluyor, bir saving oluyor.
in this particular design, we had to take advantage, for the code-based design to work with these dimensions, we had to take advantage of higher concrete strength. So this is 40 megapascal, this would be 55 megapascal. So with a objective-based design, we can just work with the same concrete strength throughout. So that's another advantage.
Evet, beton mukavemetiyle de ilgili bir yorum var. Burada 5900 PSI ile bütün bu tabii sistem çalışılabiliyor. Fakat Codebase'de aşağı yukarı 8000 PSI'ye kadar bir gereksinim duyuluyor.
And because of the reduction of number of bays in each direction, with the objective-based design, we would see some cost savings, both in terms of the volume of concrete, but also in terms of the total weight of reinforcing steel that you'd have to use in the design.
Evet, bir ekonomik bir tasarruf olduğu aşikar.
And then, the beam rotations in the objective-based design were a little bit larger, so we did have a little bit larger plastic deformation than the code-based design, but they still complied with the code objectives and were still very, very reasonable. I think the maximum was 1.6% rotation there. So we were able to achieve slightly larger deformations, but overall a much better and cheaper design.
Evet. Tabii ki bu OBD'deki durumda biraz daha fazla deformasyona maruz kalsa da binamız göçme durumunda bir yani performans açısından bir problem yaşamadık.
Questions? Discussion? Please.
Did you estimate the difference in acceleration between the objective-based design and the code-based design?
The models gave similar accelerations in this particular.
So there was no reduction in acceleration?
The peak for that earthquake, with that, it had a very big spike there, was pretty similar. Yeah, about 0.7 G. But often, yes, you would see also a reduction if you have a reduction in the base shear, you would also see a corresponding reduction in the floor accelerations. But in this nonlinear time history analysis, they were very close.
Evet, ivmelerden bahsetti hocamız. İki metot arasındaki ivme aslında aynı dedi. Fakat tabii düşmesini beklerdik dedi. Ancak bu nonlinear analizde bunların aynı olduğu saptandı.
I wanted to understand in some specific points how do you manage the strong beam, big column philosophy in your design? Could you give some information about it?
Yes, I mean you can. Sorry.
Değil mi? Güçlü kolon, zayıf giriş prensibini burada nasıl uyguluyoruz?
Yes, when you're doing your checks in selecting your beam and column sizes, that's implicit already as you're coming up with the initial sizes. So I do, and I have heard that often in Turkey, your beam widths and column widths are similar, right? Here, if you see for our moment resisting frame, they do not have the same size, our column is larger. And then we do check as we are putting the reinforcing steel, but if your column is already larger, if you're working with a 1% drift, 1% reinforcing steel ratio, you would expect to see a larger capacity straight away. But we do have to check that the capacity in the column is at least 1.2 times the capacity of the beams.
I noticed on your deformation plot, you had showed hinges at each floor.
Definitely. Yep.
Don't you have a hinge at the base of the column?
In this model, there was no hinge put at the base of the column.
There was no hinge put there.
No. Yes.
that would happen.
Yep. The beams were only put in, the hinges were only put in the beams, but yes, you'd have a hinge also at the base.
That was where they were allowed by the computer.
Yep.
Intelligent computer.
They took out the hinges at the columns.
Any plastic hinge in column? Any no plastic.
Right, so as
We tell
Bob
the
was-
computer not to sort of, see hinges in the columns.
Yes, you should. In the next step of the model, and in a more detailed model, we would add additional hinges, and you would expect to see a hinge at the base of the column.
Evet, burada sadece tabii kirişlere bir mavsar yerleştirdik ama tabii ki daha
It was
detaylı
not
bir
a-
çalışmada her yere mavsar yerleştirmemiz gerekiyor.
Plastic hinge wasn't put only at the base of the column, it was put in the upper floors, but didn't go to plastic hinge.
In this model, right, and in the interest of time of having these results and the columns are modeled with 0.7 high growth, but the hinges were not assigned in this model. Yes. Everything else being the same.
It means that
Yes.
that practice section for the definition of stiffness columns, but you didn't set any plastic hinges at the corners of the columns.
In this model, no. Yeah. In most models, we would. In this model, no.
Evet. Ümit Bey.
I have a few questions.
Sure.
One was about the crack section stiffness, as Professor asked. You use 0.7, which is the initial condition for the strength-based design.
Yep.
In the Turkish code, we do some calculations for the multiplier, let's say. So that is much lower. What do you think about it? Do you have this in ASCII 7 also? For nonlinear times 3 analysis, do you still use the 0.7?
Yeah.
Do you do some calculations?
Sure. If it depends on the software and the model that you're using, right? If it is a model like this or concentrated hinges, then in the columns we use 0.7. Yeah, no calculations.
Do you have the gravity members in the model?
In this model, no. So we would have to check the deformation compatibility. You could add in the model all the gravity members as well.
That's why I asked it, because you have the chance to have plastic hinging in the gravity members.
Yes, and we have to check. We have to check both from a moment curvature analysis of the section, right? Or you put it into the model, and you'd have to model the hinges as well.
Okay, my last question is about, are you considering the P delta effects as you're lowering your drifts?
Yes, P delta always on.
And finally, Professor, it's not a system that we allow to use in the Turkish construction industry. Because research doesn't allow us to use a system like this. And it's a dual system with frames and gravity members, which we don't typically use. So I believe that the airframe action is quite important in this one, to distribute the loss from all the floor to the moment twist and frames only. Do you have any recommendations on the diaphragm detailing? Any stuff that you can show us? Especially, I don't know if you will do the further examples, but it would be good if you can show us some typical detailing for precast slabs with toppings. Because that's what we use. If you don't have time.
It's a great question. Maybe tomorrow, or do you want to mention?
You know what the answer to your first question was about the secondary members? Use precast.
This is a good idea.
You don't have gravity, you don't have the secondary. I have one question about the Turkish design. I didn't see the base shear that was developed. Did I miss something? In the Turkish design, what was the base shear that actually?
I took some notes, and please correct me if I'm wrong. For the same load, I had from your design 0.08, 88 in the x direction, 0.0, so about 9% in the X direction and about 10% in the Y direction. Is that correct?
Yes. I think so.
But I think you want.
If I remember also correctly.
Yeah.
Okay.
This concept that you define as specific is not event specific. It's a sort of idealization of main earthquakes. What I noticed is that when you define as specific by spectral velocity, it's event specific from the now. So do you always do that, or would you, for example, would you have to convert our acceleration spectra to velocity spectrum by using angular frequency, and could you use that as an idealized setting?
Did everybody understand the question?
Arkadan çok iyi duyarım var burada konuşanları. Özetleyebilir misiniz?
Bir daha tekrarlar mısınız? Ben başka bir şey düşünüyordum. Pardon.
Türkçe söyleyeyim.
Söyle daha iyi olur.
Depremselliği biz sadece bir deprem hareketi
Özelinden değil.
birden fazla depremin idealizasyon olduğu için bizim bir spektrumumuz. Onlar sadece bir deprem hareketinin hız spektrum değerini kullanıyorlar. Sadece bir deprem. Bunu sordum. Yani nasıl sadece bir deprem seçmek de çok kolay şey değil çünkü her bina ve zemin için. Biz kendi tepki spektrumumuzu şartnameli tepki spektrumunu şeye dönüştürüp, hız tepki spektrumunu dönüştürüp onu kullanabilir miyiz bu yöntemleri sordum.
So the answer is yes. You can define your code spectrum and then dividing by the angular frequency, compute it into a spectral velocity, which was what I did for this. So the building, so even though we used the specific tonality so that we could have a comparison between the spectra and the ground motion, that's why we use specific tonality, earthquake. The building was initially designed, where the Denali parameters came from, was initially designed for a site in California that had these parameters for response spectra. So SMS and SM1 are the maximum considered spectral accelerations that tie our response spectra. So I'm trying to remember the numbers that you have. It's DD1, DD2, and DD3, right? And so the MCE level is which one? DD1. So these are the parameters, SMS, SM1 are the DD1 parameters, divided by 1.5 are the DD2, so that's the 1.4G. So with that spectral accelerations, we developed the spectral velocity, and that's the one that's there at the bottom. So you can do for any site and still be compliant with whatever design spectra you have to start off with. Good question.
One more question. Back to the fact that people say the engineer is free to choose it as far as he checks or he or she checks the relativity with the nonlinear transfer analysis, right? For example, you could have chosen, I don't know, 9, 7, and use it in the design as far as you check it later that it complies with the
Yes. Here, just because we also wanted to be consistent with the definition, the second bullet point there, a special reinforced concrete moment frame. By code, the R factor is 8. We're using a ductility factor, but it's not by chance that I use the same, right? R factor. So I used that value as a reference. But you could use another and then check with your nonlinear time history analysis. You have to have that agreed with the city or the jurisdiction if it goes outside of what's defined as a special reinforced concrete moment frame, because that's what's in our table, where we have the R factor and the overstrength factor. So we use the R factor from that, and then for all the capacity-based checks, I can also use the same overstrength that's already defined for that particular system. Sorry for the long answer. There's a few more there as well.
Planner or two-dimensional. What do you think about the intentional torsion or accidental torsion? Do you
Yeah, so we accounted, and we did have 3D analysis. It was a 3D model, and we accounted for 5% eccentricity as well. Yeah.
It made it possible in your
Yeah.
scenario.
Yeah.
Could you just show those two response spectra that you see? This is where the problem comes. The upper chart on acceleration, if you vary your period from 1.5 to 1, your strength requirement increases 100%. And the velocity, it changes nothing. It's constant. See, if you go from 1.5%, if you miss the period by 50%, the strength requirement increases 2/3. So you have to be very precise about what the acceleration spectrum is and what your behavior is. Objective-based design takes it back to where it's constant. You don't have to worry about what your period is. You estimate it, you get your forcing function, if you're off,
It's still constant.
that's the big example. I mean, that's the big.
I think there were two more questions that I saw.
Bu veriyorum hesaplamasında bir %15'lik büyütme var. Bu %15'in kaynağı, yani burada bir deneysel bir çalışma var arkasında, yoksa sezgisel mi, zaman içinde evrilen, gelişen bir şey mi, onu merak ediyoruz. Ve yine kendi içinde bir soru, taban kesim kuvvetleri dağıtıldıktan sonra donatıların tayininde sezgisel bir, yani tecrübeye dayalı bir donatılandırma yapılıp sonra şey ediliyor, yoksa orada tamamen kuvvet, yani mekanik bir
Evet. In terms of periods, we increased the periods by 15%, let's say. So is this like an intuitive thing, or why did you do it? And the second question would be if the base shear, when you increase or for the change in the base shear, the reinforcement also changes. So, but is there an intuitive approach for the reinforcement, or you keep like a constant, like 1% or so? I mean,
Sure.
if I understand the question
Yeah.
correctly, yes.
So the first question on if you go back to the SSRP report, the target was also 1.5, and then the actual from the response of the building was closer to 1.59. And that was one example, just to give you context, right? But you would expect to see slightly different changes in the real structure versus in your model. And a shift of about 15% is based on literature, based on intuition, but it's informed intuition. For the second question,
So, sorry, is it related with the estimation of the nominal behavior of the structure?
Yeah.
Direct.
Yeah.
It means increment of the predominant period during the execution of the structure changes on the structure.
yes,
To
to represent the actual behavior, yeah, and the period shift that you would expect to see in the response of the structure. Yeah, that's one. On the second one, the goal is around, which I think is similar, at least from your designs, the goal is around 1%, right? And then as you're actually detailing it, it's going to be close. But having 1%, we know that we're going to have well-formed hinges, good ductility, and it's not a balanced design in the sense of moment curvature balance, but a balanced design in terms of a good design. So we try to hit very close to 1% in terms of the reinforcing storage.
All sides of the beams and columns to make some limited amount of reinforcement placement in the cross section. In that case, do you think about the architectural restrictions for this point?
Sure, but I think, yeah, we do, but I think in terms of column sizes, let me see. Now I have to do a translation here. What do we have? This is code-based, this is objective-based. So we're getting, and please correct me if I have the wrong dimensions. I took note of your dimensions, but please correct the dimensions. So you had 4 different sizes. I'm going to start with the larger, was 95 by 95 cross-section, correct? And so this was 4 columns. And we have, where's our column? 76 by 91, right? So we are accounting for the dimensions, and yes, you'd have to check architecture as well, but I think they're very close to the dimensions that you were getting as well. The smaller was 75 by 95. No, you had the 75 by 85 and 76 by 91. One question that I had, so in terms of dimensions, I think we're close in terms of what you were getting for your, so it's not that we increase the sizes, we can still match the 1% with the initial sizes that were decided based on the portal method. You can also check with your SAP or ETABS model in terms of what those dimensions are and do your checks. But with this idea of having about 1% reinforcing steel ratio for your design. Oh, that was beams. And then you had 90 by 110. No, that's when you started. 90 by 110, but that's with the larger load, and then you came down with the 7.2. Okay, so check. All right.
Assume that secondary members, that is, vertical load carrying members, are not going to participate in responsibility because their strength and performability is so much less than the bracing system. How we account for it is to make sure that the secondary members are designed to be done. In other words, the shear capacity exceeds the moment capacity. Places of the expected regulation are in B which decline as though they're going to go through the rotation. So we like them analytically, we deal with them as they were performed.
Yeah. And you can.
Yes, there's one question.
So the answer was that, so we got back to the question about the gravity systems and what we're doing for the gravity system. So we don't have to account, as I have here in these bullet points, we don't have to account for them analytically. We have to check that they can carry the deformation. It's called deformation compatibility. Whatever deformation you're going to see in your moment resisting frame, you have to have the same deformation capacity for your gravity connections, right? And so for the columns and the beams. So you still have to detail them very, very well so that they can capture that deformation, but we're not counting them on the capacity for strength. That's for the lateral resisting system. And maybe I should add that we don't consider this a dual system. A dual system would be a dual lateral resisting system, but I understand what you mentioned. You can also, so my third bullet point there, you can also explicitly model them, right? But often they're not considered in the modeling and they're not considered analytically, but we check that all those connections can withstand the deformations. Yep.
First answer was still right. Use precast.
Do we have time for more questions? There's two more questions.
There's 2 questions actually.
2 questions, yeah.
You have to involve like 2 lateral load resisting systems in moment plane. But distance is nearly 64 meters. In Turkey, we are doing for shear walls maximum 40 meters for diaphragm action. How exciting if you ask me for the lateral moment system, are you put also middle of the flash in case state? earthquake loads?
Mm-hmm. Yeah, so we would have to check the diaphragms, right, and design the diaphragms as well. And if you look with the dimensions that we would have that the diaphragm in the x direction is not flexible, can be considered rigid. The diaphragm in the north-south direction would have to be considered as flexible. And then we design for it. Maybe one of the reasons that this works well is because we do have the 20 centimeter post-tension slabs as well as part of our design. But in the design process, we would have to check and detail the diaphragm as well. But this diaphragm would work in terms of the dimension that we have here, it would work.
You don't use post-tension slab, only convection slab without post-tension.
Sure.
It's also enough for 64 meter.
We'd have to check it. Yeah. Question.
That's where engineering intuition will never be replaced by the, what do you call it, AI, artificial intelligence. Artificial intelligence would say that was good. As a designer, I would not make my diagram span the whole length of the building. Instead of using frames at the end, I would put them distributed 4 in the middle to reduce the load on the diagram. I'm sure artificial intelligence would tell you that, but not this section.
I don't know if you heard that response. Yeah. So basically, in terms of the solution here, would be Bob was suggesting that instead of having these on the outer edges, that you'd have somewhere interior these moment-resisting frames so that the spans for your diaphragm would be smaller. So that would be part of the design process and checking. But in terms of lateral resisting load, we only need these 2 frames in that direction. There was another question here.
Can we say that this design overall has more reflection, like more plastic hinges and beams, and more solid of the column at the base of the column in the event of an earthquake? So does that mean after an earthquake we need to repair this kind of system?
So in terms of this, for example, the estimate of the residual displacement, let's start with that. And I think it's a proxy for the question that you're asking. For this code-based design, for example, we would have 0.5% residual drift at the end of the earthquake, right? For this one. And for the objective-based design, we have 1%. So yes. So if you also relook at some of this beam would have 1.3%. This would be 1.6%. Honestly, within the range of design, 1.3 and 1.6 is the same for me, right? But yes, you would have a little bit larger deformations, which I think we've summarized it here as well.
So maybe we say that we will see some
Damage.
cracks that are not structural, that means repair for corrosion.
Not really, because this is for the earthquake load, right? And if you, I mean, you have here professors who do a lot of testing. After you do your testing and you have your cracks, at the end of the test, if you don't have concrete spalling, your cracks mainly close. If we're talking about 1.3 to 1.6%, we're not talking about 4%, 6% interstory drift ratios. We're talking about 1% interstory drift ratio. And I don't know what your opinion would be, but most of these cracks after the earthquake would be mainly closed. It sounds like a lot, but it's not, because these can take 4%, 5%, 6%. If you look at some testing, yeah, it's really low.
Yeah, what about like after a couple of earthquakes, that will there be still
Yeah, so do not look at the strains of the reinforcing steel, but I wouldn't expect at this level of drift that we would start seeing fatigue of the rebar, because the strains are still rather limited for 1.3 to 1.6 rotations.
Don't worry, we have a 588-page book coming out today. What to do?
Evet, 588 sayfalık bir şeyimiz var zaten diyor.
There's some more
Bakalım
questions?
istiyor.
One more?
Buyurun.
Deprem etkilerinin tanımlanmasıyla alakalı herhangi bir şey var mı? Bir görüş şu anda.
In terms of the vertical earthquake action, do you have any comments on that? Vertical
Yeah.
accelerations.
I have many comments on vertical accelerations. Yes, you should include them. That's my personal opinion. We should include them in the analysis. We should include them in the design. If I trust the numbers that are used, I don't know if I do. And it really depends on where you're located. And I think Bob explained how for the Northridge earthquake, there was a considerable vertical acceleration that was not accounted for in the design detailing, and that may have helped explain the failures. In Christchurch, there were huge vertical accelerations, about 2G. In Japan, for some of the subduction zone earthquakes and close, vertical acceleration is also important. Now, for your lateral design, I don't think it matters too much. But as you're designing your building and as you're designing your different systems and connections for cladding, for precast connections, or other connections, yes, you should be accounting for vertical acceleration. That's my opinion.
Well, have you ever experienced an earthquake?
We all did, I guess.
Yes.
The vertical wave arrives directly from the source. The longitudinal wave comes from the shaking of the mountain. So they're entirely separate. I used to have fun in Los Angeles in high-rise buildings. I would feel a vertical acceleration, and I'd look around to see the reaction of the people when the horizontal wave. But it always comes first, logically, because the wave comes vertically. And there's a line around it. The vertical wave and the horizontal wave both come from the same source. The vertical wave comes straight up. The horizontal wave comes from the impact of the movement on the soil. So they're usually separated by a couple of seconds or so. I used to have fun sitting in a high-rise building, feeling the vertical. Then I could look around and watch the reaction of the people when the horizontal wave came. You want to know how close I came to death? In an earthquake. It was a Northridge earthquake. Vertical wave came, I felt it. So I protected myself because when the horizontal wave came, my wife jumped out of bed and started jumping on the mattress. And so I was really concerned about my kidneys, nothing else. So that's the answer to your question. They are separated, so it really is the rational reason. Understand them? Yes, because the vertical wave, as I showed you in the Northridge earthquake, it demolished the system before the horizontal wave came. And as you can see, the horizontal wave, the columns were still standing. Just standing, well, it was the vertical load carrying system was not reinforced to take the up and down thing.
What do you use for vertical in Turkey? What vertical accelerations do you use?
We have a defined also spectral acceleration for that.
Okay.
So you calculate the
And it's based on.
some formulas also.
Okay.
Yeah.
Okay. So a percentage. So 20% times some factor. Okay. Okay.
They don't impact the system in the same way.
Right.
Nor do they occur in the same amount.
Yeah.
Yes, one should have to help.
Yeah. The national document of the Eurocode in Portugal specifies 30% for vertical acceleration, and that makes no sense to me. That's another magic number that nobody knows where it came from. They're all magic numbers. Yeah, exactly. Yeah. Yeah.
Evet, o zaman
Any more questions?
soru yoksa bir 20 dakika ara verebiliriz. I think we can take a break for 20 minutes.
Thank you.
Because we are a little bit behind our schedule, but still, that's fine.
But I think it was good for the discussion. Thank you.